In Unit 2B, we are going to talk about vectors. So far, when we study transformations, we've talked about transformations by looking at a graph, we've talked about transformations using words, and we've talked about transformations using a coordinate rule. And now we're going to start talking about transformations using vectors. Before we can talk about transformations with vectors, we need to understand what vectors are. So our definition for a vector is that a vector is a directed line segment that has both magnitude and direction. When we say magnitude, we mean how long. When we say direction, we mean in which direction. Up, down, left, right. What does it look like? A vector is represented in the coordinate plane by an arrow drawn from the initial point to the terminal point. When we say initial, we mean beginning. And when we say terminal point, we mean end. To terminate something means to end something. So let's take a look and see what this looks like in the coordinate plane. Now when you see this looks like ray FG. But notice, this is an arrow that actually has an ending point. It ends at G. So we go from point F to point G. To denote that, we have vector FG. Notice that this symbol above FG is not a ray. This is called a harpoon. The letter that comes first is always your initial point, and the letter that comes second is always your terminal point. So vectors are different than rays because vectors have an end and rays would go on forever, even though they look very similar in a coordinate plane. Another way to denote a vector is with a bold lowercase letter. That's difficult to do when we are writing by hand, but when I give you worksheets, you will see that in worksheets sometimes. So this is a bold lowercase letter, and a vector can be represented by that. So let's talk a little bit more about this vector. The vector has an initial point F, terminal point G, and we can name the vector like we did over here, and we can also talk about the component form of a vector. The component form of a vector describes the direction by combining the horizontal and vertical components. Let's see what I mean by that. The horizontal component would be how far am I going horizontally? So from F to G, excuse me, I go from -2 to 4, which is right. 6 units. That would be my horizontal component. Rewrite that first. 6. My vertical component is how far I'm going vertically. I'm going down 1, 2, 3, 4, 5 units. So my vertical component would be -5 to show that we are going down. So you put a comma here. You don't not put parentheses. If we put parentheses, you'd be talking about a point. Instead, you put these little arrows. So remember, it is always your horizontal component, comma, your vertical component. Now here, it was easy enough for us to count, but I do want to talk about a way that we can figure out the horizontal and vertical components without looking at a graph. In order to do this, let's think about our horizontal component. We traveled right 6 units. We could have gotten that by taking the x coordinates of our 2 points and subtracting them. We always start from our terminal point and subtract our initial point. So we could have done 4 minus -2 and gotten 6. Or for our vertical component, we could have done -3 minus 2 and gotten -5. Please note, we always do terminal minus initial, where you end minus where you started. All right, and then finally we talk about the magnitude of a vector. Now magnitude is how long a vector is. So the magnitude is the excuse me, length of the vector. So magnitude is just another word for length. We denote that by taking your vector FG with the harpoon above it, and we put these what look like absolute value bars, but 2 on each side. That is magnitude. So let's think about that. To find the magnitude, if we look at this, well, we have kind of a right triangle. And we know that in order to find the hypotenuse of a right triangle, we simply use the Pythagorean theorem. So if this is your right triangle, this length is 5, this length is 6, and then our hypotenuse will be the magnitude of vector FG. So looking at this, the magnitude of vector FG squared will be equal to 5 squared plus 6 squared, or the magnitude of vector FG squared will be equal to 61. So in order to find the magnitude of vector FG, we take the square root of 61. Now, this is the exact answer. Remember, unless otherwise specified, an answer or a problem always wants exact answers. However, it could tell you to approximate. And let's say I asked to approximate to the nearest hundredth. What you do is punch that in your calculator, and you'll get that this is approximately 7.81 units. So it's important to remember the difference between exact and approximate. And that is our introduction to vectors. Now go ahead and pause the video, and I want you to practice with these vectors. Now that you've practiced with the vectors, let's look at example 1. Example 1 says, name the vector that is contained in the third quadrant and write its component form. Remember, this is quadrant 1, 2, 3, and 4. So the only vector that is contained in quadrant 3 would be vector AB. We name that with the initial point A, terminal point B, and our harpoon. The component form would be our horizontal component, comma, our vertical component. Well, to go here horizontally, I do not move left or right. So our horizontal component is 0. Our vertical component, I go down 3, so that would be -3. Now I could have gotten 0 by looking at the coordinates. A has coordinates -3, -1, and B has coordinates -3, -4. So to get my horizontal component, I could do my terminal minus my initial and get 0. And for the vertical component, I could do my terminal minus my initial and get -3. So remember, I'm not going left and right at all horizontally, but I am going down 3 units, so we get a -3. Now finding the magnitude. The magnitude here is easy. The reason why it's easy is that this is a vertical line. Remember, vertical and horizontal lines, we don't need to draw a right triangle and use the Pythagorean theorem. We simply count. The magnitude of vector AB is equal to 3 units. Go ahead and try example 2 if you have not done so already. Now that you've tried example 2, let's talk through this. I want you to name a vector that is in both quadrant 1 and 2, write its component form, and find its magnitude. Well, let's look at this. We have actually 2 vectors that are in both quadrant 1 and 2. We have vector PQ, and we have vector MN. Now PQ, our horizontal component, is right 1, 2, 3, 4, 5, 6. So this would be a +6, comma, our vertical component is up 3, so +3 for our vertical component. MN goes from the initial to the terminal point down 3 and left 6. So we will go left 6 would be our horizontal component, negative 6. I apologize for the phone ringing. We're going to continue through it. And our vertical component is down 3, so minus 3. If we want to find the magnitude, we can do that again, making our right triangle with either one of these. You can draw the right triangle in here if you would like. And you'll notice that both of these triangles have the same leg lengths. So these magnitudes are actually going to be the same. So one will have a length of 3, the other one will have a length of 6, and we're trying to find the length of the hypotenuse. We can denote it like this. Mn squared, the magnitude of vector mn squared, is equal to 3 squared plus 6 squared. So the magnitude of vector mn squared is equal to 45. And if I take the square root of both sides to solve, I get that it's equal to the square root of 45. Now that doesn't specify what to round to, so it wants the exact answer. But you will not give me square root of 45 as your exact answer because this is not in simplified radical form. So if we simplify this, I know that's really equal to the square root of 9 times the square root of 5, or 3 root 5 units. Let's turn to the back. This introduces us to the concept of equivalent vectors. If you look back on the front, vector mn and vector pq were equivalent vectors, and I want to talk about what equivalent vectors means. Equivalent vectors are two vectors with the same magnitude and direction. It has to have both the same magnitude and direction. So notice that the vectors on the previous page had the same magnitude, however, they did not have the same direction. The other vocab term I'd like to introduce you to is standard form. A vector with the initial point at the origin is in standard form. So when we look at this, go ahead and do example 3 and 4 using these two new definitions. Example 3 says to name two equivalent vectors. If you have not done so already on your own, please pause the video and do this independently before you check your answers. If you have, let's talk through this. Two equivalent vectors are TC and MN, but they want us to prove they are equivalent. Well, there's two pieces of information that are important. One, they must have the same magnitude, and two, they must have the same direction. So when we look at that, their magnitudes, again, we can use the quadratic formula, we can use the Pythagorean theorem, and you find that each magnitude is 3 root 5 units. So because their magnitudes are equal, they is one of the two requirements for equivalent vectors. The other thing is that they need the same direction. And in order to look at that, we can look at the component form. Notice that they both go left 6 and down 3, not right 3, sorry. So they have the same component form, which tells us they have the same direction. Next question says, which vector is in standard form? Well, remember, standard form means the initial point is at the origin. That would be vector RS. Make sure the R comes first, and then the S, your initial point, and then your terminal point. Now we want to talk about translations with vectors. Translations with vectors look very similar to that of coordinate rules. We're going to take this triangle ABC, and we're going to translate it using the vector -4, 1. Well, picture this like xy goes to x minus 4, y plus 1. It's the exact same thing, except now it's written as a vector. Go ahead and do this on your own right now. If we look here and we graph triangle ABC and we translate left 4 and up 1, here's triangle A prime, B prime, C prime. So here's our vector, or each one of these represents the vector, and here's our translated triangle. Make sure to use prime notation when you are denoting this. Part B says, how far did you translate triangle ABC? Well, think right now, what would you have to find in order to figure out how far it is translated? If you said magnitude, that would be correct. We find the magnitude of this vector. So if we find the magnitude of the vector, we know that we go up 1 and left 4. Well, here's the Pythagorean theorem. We know that triangle ABC is translated square root of 17 units. That would be the exact answer, again, because it doesn't tell us what to round to. Let's take a look at example 6. Example 6 now gives us the image already, and it wants us to figure out what is the vector that will transform triangle ABC to triangle A prime, B prime, C prime. Well, when you look at this, you have to ask yourself, what is the transformation? Go ahead and do this on your own right now. Hopefully you noticed that the units were going by 2. So the vector that will transform this will be the vector that translates this triangle 1, 2, 3 units to the right and 2, 4 units down. So we want to go right 3 and down 4. The vector to do that would be positive 3, comma, negative 4. When I asked how far is triangle ABC translated, I hope that that tells you that you need to find the magnitude of the vector. And again, if you go right 3 and down 4, you would have a triangle that looks like this. Then we would have x squared is equal to 4 squared plus 3 squared, or x squared is equal to 25, or x equals 5. So how far is triangle ABC translated? 5 units. Here's your introduction to vectors. We will continue this in class in the future.